Good evening everyone. So welcome to my YouTube channel Maths Subgram. So today we are going to see third lecture on linear transformation. So today we will study what is isomorphism. Let V and W be two vector spaces over the same field. Then a linear transformation V to W is said to be an isomorphism if first P is 1, second P is onto. So, so Problem 1, let V and W be two vector spaces over the same field F. If PV to W is an isomorphism, then P inverse W to V is also an isomorphism. Proof. So PV to W is 1 and onto. So this implies P inverse W to V is well defined 1 and onto. Next, let W1, W2 belongs to W and alpha beta belongs to field. Since W1 belongs to W, there exists unique V1 belongs to V such that PV1 is equal to W1. It means P inverse W1 is equal to V. Similarly, W2 belongs to W. There exists unique V2 belongs to P such that P02 is equal to W2. It means P inverse W2 is equal to V2. Now, P alpha B1 plus beta B2 is equal to alpha sin PV1 plus beta times PV2. Because T is a linear map, we will have this property. What is this? This is W1, this is W. So this implies T alpha and beta is equal to alpha W1 beta W2. So this implies P was alpha W1 plus beta W2 is equal to alpha V1 plus beta V2. But what is this? This is P inverse W1 plus beta inverse W. So this implies P inverse alpha W1 plus beta W2 is equal to alpha P inverse W1 beta P inverse W2. So this implies P inverse W2 is a linear transformation. We have P inverse P inverse W2V is a linear transformation. One and on to this implies P inverse is an isomorphic. Okay. So corollary that V and W be two linear transformation over D2 vector spaces vector spaces over the same field F. Then P V2W is an isomorphism if and only if P inverse W2V is an isomorphism. So first assume that T V to W is an isomorphism. Then by theorem 1 we get P inverse P inverse W to V is also an an isomorphism. Okay, so first part is done. Conversely, assume that P inverse W to B is an isomorphism. Then by theorem 1 we get P inverse V to W is an isomorphism, but P inverse is nothing but P. We conclude T V to W is an isomorphism. Isomorphic 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 vector spaces. Let V and W be two vector spaces over the same field F. Then we say that V is isomorphic to W if there exists and this a linear transformation T V to W there exists if there exists an isomorphism PV to W. Okay. If V is isomorphic to W, V denotes it by V isomorphic to W. Remark, if V is isomorphic to W, then W is isomorphic to V also. If V is isomorphic to W, then there exists T V to W and isomorphism. This will imply P inverse W to V is also an isomorphism. Okay, so it means what? V is isomorphic to W is isomorphic. Okay. This is remark 1. So remark 2, V is isomorphic to W if and only if W is isomorphic. Okay, so we can write this because V is isomorphic to W, then W to P, and W is isomorphic to V, we can write W is isomorphic. Okay, theorem 2. Let V be a vector space of dimension V be vector space with dimension of V is n, that is less than. It means V is a vector space of finite dimension over the field then V is isomorphic to Fn of let V be a vector space with dimension of V is equal to n, that is finite, over the field F. Consider V is equal to V1, V2 up to Vn, basis of V. Okay, we know that Fn is equal to alpha 1, alpha 2 up to alpha n. Alpha I belongs to F. Is a vector space. Is a vector space over the field F. Let V belongs to B. Then there exists unique scalars alpha 1, alpha 2 up to alpha n belongs to F such that V is equal to alpha 1 V1, alpha 2 V2, alpha n. We write PV is equal to alpha 1, alpha 2 up to alpha n. That belongs to Fn. Okay. Then P V2 W defines a map. Now we check P is a linear transformation. So let V1, V2 belongs to P. Then V1 is alpha 1, V1 alpha 2 V2 plus alpha n Dn and V2 is equal to beta 1 V1 plus beta 2 V2 and Dn. Let alpha beta belongs to field. Then what is alpha B1 plus let alpha B1 dash B2 dash. So B1 dash B2 equal to this. So alpha V1 beta V2 dash it will be equal to so alpha 1 beta 1 V1 plus alpha 2 plus beta 2 V2 alpha n beta n V. So this implies P alpha B1 dash plus beta B2 dash is equal to alpha 1 plus beta 1 alpha 2 plus beta 2 alpha n plus beta. So how we'll write it? alpha, alpha 1, alpha, alpha 2, alpha, alpha 1, beta, beta 1, beta, beta 2, beta, beta n. So this is alpha, alpha. You can write like that. So what is this? This is nothing but T V1 dash. And what is this? T V2 dash. So this implies take alpha V1 dash plus beta V2 dash is equal to alpha T V1 dash beta V2 dash. For all V1 dash V2 dash is to be and alpha beta. So what is the meaning of this? This means T is a linear transformation. Now P is 1 1. Let P V1 dash is equal to P V2 dash. Then this implies alpha 1, alpha 2, alpha n is equal to beta 1, beta 2, beta n. So comparing both these, I will say alpha 1 is beta 1, alpha 2 is equal to beta 2, and so on. Alpha n is equal to beta n. Alpha n is equal to beta n. Now V1 dash is equal to alpha 1 V1, alpha 2 V2, alpha n V. So alpha 1 is beta 1, alpha 2 is beta 2. So what is this element? This is V2 dash. So V1 dash is equal to V2 dash. So this implies P is 1 1. Okay, P is on. Let W belongs to W. Sorry. Let alpha 1, alpha 2 up to alpha n belongs to Fn. Then put V is equal to alpha 1 V1, alpha 2 V2, alpha n Vn. So this will belong to V. Then PV is equal to alpha 1, alpha 2, alpha n. So this implies P is on. finally, we have shown that V2 Fn is a linear transformation which is 1, 1 and onto. Hence, V is isomorphic Fn. So this is true. Proposition let V, W and Z be three vector spaces over the same field F, and let P, V to W and S, W to Z be isomorphic. Then S compose P is composed P. V to W is an isomorph. So P, V to W is 1, 1 and onto. S, W to Z is 1, 1 and onto. So this implies S composed P in V to Z is 1, 1 and on. So let V1 V2 belongs to V and alpha and beta belongs to F. Then S composed P alpha V1 plus beta V2 is equal to S P alpha V1 plus beta V2. So what is this? This alpha times V1 plus beta times P0 because P is a linear map. Again apply S is a linear map. What we have? We will have this. So we have S composed P alpha V1 plus beta V2 is equal to alpha S composed P V1 beta S composed P V2. For all V1 V2 belongs to V and alpha beta belongs to F. So this implies S composed P V2 Z is a linear transformation. So this implies finally we have shown that S compressed T into Z is a linear transformation which is 1 and only 2. So this implies S compressed T into Z is an isomorphic. Showing that V and W be two vector spaces over the same field F. Then V is isomorphic to W if and only if dimension of V is equal to dimension of W. We assume that dimension of V is equal to finite and dimension of W is also finite. Okay. First, assume that dimension of V is equal to dimension of W is equal to n, that is okay. 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 Since dimension of V is equal to n by theorem 1, by theorem 2, V is isomorphic to Fn implies there exists P V to W, V to Fn isomorphic. Similarly, dimension of W is also n by theorem 2. W is isomorphic to Fn implies there exists S W to Fn isomorphism. It means S inverse Fn2 W is an isomorphism. Now, then S is equal to S inverse composed T. V2 W is an isomorphism by proposition. Therefore, this is S inverse composed T by proposition. Hence, V is isomorphic. Conversely, assume that dimension of V is isomorphic for W, then there is an isomorphism T V to W that dimension of V is equal to N. Consider V1, V2 up to Vn basis of V. Put W1 is equal to Tv1, W2 is equal to Tv2, and so on. Wn is equal to Tv. And B dash is equal to W1, W2 up to Wn. We claim that B dash is a basis for W. Number one, B dash is linearly independent. That alpha 1, alpha 2 up to alpha n belongs to F such that alpha 1 W1 plus alpha 2 W2 alpha n Wn is equal to 0. Then what is W1? It is Tv1 alpha to Tv1 plus alpha n Tvn is equal to G. So what is, by property of linear map, what we have? Alpha T1 alpha T2 alpha n Tn. P is 1, 1. Since P is 1, 1 and P at 0 is 0, we get alpha B1, alpha 2 B2, alpha M B1 is equal to 0. Since B is equal to B1, B2, Bn is basis for B implies V1, V2, Vn are linearly independent. Therefore, alpha V1 plus alpha 2 V2, alpha M Vn is equal to 0 implies alpha 1 is equal to alpha 2, alpha m, all are 0. So this implies W1, W2, Wn are linearly independent. So this implies D dash is linearly independent. Now second is W is the span of B dash. Let W belongs to capital W. Okay. Since P is on to, there exists B belongs to B such that P is equal to W. Now B belongs to B and B is basis for B. It means B is the span of B implies there exists alpha 1, alpha 2, alpha m belongs to F such that B is equal to alpha 1 B1 plus alpha 2 B2 alpha m B2. Then W is equal to P B alpha 1 B1 alpha 2 B2 alpha m B2. This is alpha 1 P B1 plus alpha 2 P B2 alpha m P B1. So this is alpha 1 W1 alpha 2 W2 alpha m Wn. So this implies W is equal to alpha 1 W1 alpha 2 W2 alpha m W. So this implies W belongs to span B dash span B dash. So this implies W belongs to span B dash 4O. W belongs to capital W. So this implies W is span so W is span of B dash. And finally, we have shown that B dash is linearly independent and W is span of B dash. So this implies B dash is a basis for W. Now, therefore, dimension of W is cardinality of B dash, that is nothing but number of elements in B dash, that is n. But this is also cardinality of B, that is dimension of, so this implies dimension of B equal to dimension of W. So reverse part is also proved. Okay. So question are Rm and Rn, they have M is not equal to M, isomorphic to each other. Solution answer is no. Answer is no. So dimension of Rn is equal to M, that is not equal to M, that is, and what is dimension of Rn? Okay. So this implies dimension of Rn is equal to dimension of Rn. So this implies by theorem 3, Rm is not isomorphic to Rn over R. Okay. So going back to this, if you have any problem related to this, you can comment on my section. Like, share, comment, and subscribe my YouTube channel. So thank you very much for today's lesson. Thank you. We will see you on next.